So now that we're through with our functional analysis lecture series, we can finally use what we've learned and start to analyze the prototypical equations that we saw before. Now, so this is a short summary of everything from the last lecture series. And we're looking for a solution U in some space, a function space, such that this equality holds for all these test functions, also in that space. And here I have in green box an example that has nothing to do with fluid mechanics. This is your typical Poisson equation, for which we would write the weak form in this manner, and you would have forcing on the right hand side, right? So then the V in this equation here would become the space H10, and we have this bilinear form defined as this integral of the gradient dot the gradient, and a linear form. And what we learned so far is that to understand these equations and to be able to say things about existence, uniqueness, and stability of solutions, there are two core concepts, and those are the one of coercivity and boundedness. And we start off already getting sort of a feel of what these mean, specifically coercivity. They sort of had an eigenvalue interpretation, smallest eigenvalue interpretation, it had an interpretation in terms of the natural stability of the bilinear form. And since the bilinear form is really just a way of encoding the differential operators, it has a stability of a differential equation embedded into it. Or that's what the constant C sort of resembles, the stability of a partial differential equation. So now that we've done all that, let's try to use that knowledge and get back to the prototypical equations and see what we can find out. And I'll actually start with the Stokes equations, because that's a relatively short story, as you'll see in just a second. And then I'll have a couple of additional videos on the advection diffusion equation. Now remember, the Stokes equation was a prototypical equation that had this mixed set of variables, a solution field U that describes the velocity, and a solution field for P that was the pressure. So in a strong form, the Stokes equation said, and again, there were many different ways of writing these equations, but one of them is that we have this minus the divergence of nu times the gradient of u plus this transpose gradient of u plus the gradient of the pressure being equal to body force, with the constraint that the divergence of u is equal to 0. That meant that it's an incompressible flow. And we also have another constraint, that's a boundary condition. And we're simply going to, in this case, assume homogeneous Dirichlet conditions all around. So we have that our velocity is set to 0 on complete boundary of our domain. And both of these partial differential equations are then set inside of the domain omega. So that's one way of writing the Stokes equations. Small thing to note here, we could rewrite this a little bit, change of notation, and make use of this is equal to twice the symmetric gradient of u, right? Remember that the symmetric gradient is equal to half of precisely what it says over there. Okay, so this is the strong form, and we said, well, actually we don't really like strong forms, we like weak forms. Weak forms have more potential solutions for more different types of data. And data in this case is really just a function f, right? That's the right hand side, but if we would have prescribed Dirichlet data, we would have something here. Potentially we have Neumann data. And weak forms are the ones that we like, so let's try and change this into a weak form. So how do we go about doing this? Well, the proposed strategy so far was by the method of weighted residuals. We're going to multiply by a test function, integrate over the domain, and do certain integration by part steps. So if we do that, then we obtain a statement like the one in the beginning. Let's first think about what our solution variables are, though, because the ones that we've had so far, we really only had one solution variable, and now we're looking for two. Well, in principle, that's really not an issue. We can simply say to look for two different solutions. So find my function u, which is a velocity field, and p in the space. And let me, just to clarify, this is going to be one space in which we have this compactified combination of a field for u and a field for p. So the way that the space V is now defined is actually, well, what you might do is you might want to take H1D for the vectors, right? D-dimensional vectors. There's D components to U, and each one of those is going to be in H1. And not only in H1, actually H1 0, right? We have the zero boundary condition. Cross the space for the pressure, and as we'll see in a second, that's going to be L2, and not just L2, but also L2 0. And I'll get back to that in a second. Such that, and then, well, because we have two equations, we sort of also have two equations here, although you can, in fact, actually just add them together. It doesn't really matter. You know what, let me add them together. Then we have this equation that most clearly is analogous to what we have here. Okay. So what I'm going to do is I'm going to multiply the first line strong form by a test function v, and this is a vector equation, so I have to multiply this by a vector test function as well. So I'm gonna integrate it over the domain. So then I have the integral over the domain of this term multiplied by v, or dotted with v, plus the gradient of p dotted by v is equal to this term integrated over the domain dotted by v. Then I'm going to do integration by parts. I can use the divergence theorem that we also saw before. That's going to move derivative operator onto the test function, and the same thing actually applies here. And I'll just give you the result already. This is going to be the integral over the domain of, well, what I'm left with is twice the symmetric, or twice the mu times the symmetric gradient of u, right? That's essentially what this is, twice the symmetric gradient of u times mu. But now dotted with, and actually double contracted with, the symmetric gradient of our test function v. Plus, no, minus the integral over the same domain of p, and I've also done the divergence theorem of this term, or the integration by parts, which actually uses the divergence theorem, such that this ends up being p times the divergence of that test function v. Okay, so that's my first equation, the left-hand side. The second equation, I'm going to multiply by a different test function. Well, this is a scalar equation, so I need a scalar test function. I'm going to multiply that by q, integrate it over the domain, and then I can just add it to this equation. Or you know what, let me subtract it, because then we see that this is actually going to be symmetric. So now we have q times this expression, divergence of u. And on the right-hand side, what we're left with is, well, the first one minus the second one. The second one is 0. So we have the integral over the domain of our vector-valued body force dotted with our test function v. Okay, and this has to be true. This equality has to be true for all our test functions. Well, what are our test functions? These are v and q in the space, well, in the same space, v, which was defined as this vector space of components in H1 across L0, L2, 0. So now we see that this, even though we're dealing with a mixed form, right, we have two different variables here, a u and a p, we still end up with an equation that fits perfectly in what we have right here. We have some solution in some space. Well, our solution is now u comma p, and if you don't like the notation, I can put brackets around it, and you see that's really just one solution. It's u comma p. So that's represented by u here. And you know what? Let me. I'm going to change my variables here so you don't get confused. There you go. So Now you should think of u comma p as my unknown field phi here, which lives in some function space. Well, our function space is still just v, but it's compiled of this vector valued field and an L2 field, such that some bilinear form, and this is a bilinear form, is equal to a linear form for all test functions in that same space. And that's precisely what we started off with, right? So also the Stokes equation falls within what we've talked about in our functional analysis lecture series. Now, a couple of other interesting things to note here is, well, this is a symmetric bilinear form. If I swap, so this is going to be of the form find u comma p in, well, that space such that some bilinear form, the Stokes bilinear form, let's put it like that, u p comma v q is equal to some linear form also involving v q for all v q in that space. Yeah, so this is what this equation really looks like, and that's precisely what we're hoping to find. Now, interestingly, B is symmetric in the sense that if I were to swap UP and VQ in these equations, then nothing changes, right? So this is ends up being the same. So that's a symmetry notion of a bilinear form. Now, anything else interesting? Yeah, let me now define what exactly I mean by this L2 with a 0. So this is going to be the set of functions, and I'll use Q, which are in L2 under a certain constraint. And that constraint is going to be that if I integrate over the domain, then it's going to be equal to 0. So this is sort of a constrained version of the space L2. Why do I need this? Well, if we actually look at the original statement, then we find that, well, the only way that the pressure really shows up is via this gradient term. And that means that you can always add a constant to your pressure and it would still satisfy these equations, right? So if I find the solution P, then I can add 1 to my solution P and it would still satisfy all these equations. So it means that we have to sort of constrain our search for P. And the way that we do that is that we say that its integral might be 0. There's all kinds of ways of doing this. This is a very clean way of doing this. So you say that the integral of my pressure has to be 0, and that's the only potential candidates for the pressure that we're really accepting. And since we want our solution space and our test space to be the same, we also do the same thing for our test functions here. Now, another thing that I maybe should address here is that you don't see any boundary terms. So what we did was we did integration by parts on this divergence and this gradient. So that actually should give me attraction, if you're slightly familiar with the theory here. That should give me attraction on the boundary, or at least an integral that is of attraction look-alike in the sense that we have pressures and gradients of velocities on the boundary. But that is all multiplied by v on the boundary, or dotted by v on the boundary. And since we set this Dirichlet condition all around the boundary where my solution field u is 0, we're using the same space for our test functions. So our solution field for v is 0 on the whole boundary, such that that term actually drops out. Now, so I do encourage you to try this step yourself. There's also some trickery going on in the way that these differential operators now change to these symmetric ones. In order to understand that, you would have to work out the indices, which I definitely encourage you to do. But I hope that with that I've kind of pointed out all the important parts here without going into too much depth. Okay, now that all being said, this is the form of the equations that we're interested in, or that the Stokes equation show up to be. Now we want to analyze this. We want to determine if this is going to permit a solution, if there's existence. We want to see if this is a unique solution. We want to understand some stability characteristics. So to do all of that, we had this concept of coercivity and boundedness. So the things that we have to do is that these inequalities hold true. That if I substitute my same solution field in both slots of my bilinear form, then it's always going to be larger than some constant multiplied by the norm of that function squared in whatever norm is relevant to my function space V, right? And similar requirements for the boundedness. Now, for the advection diffusion equations, we're going to do this to a high level of detail. But for the Stokes equations, we actually don't need to, because we can find a pretty obvious reason. Or maybe it's not obvious, but we can find a pretty clear reason for why this is actually not satisfying our required coercivity and boundedness, and specifically coercivity. So coercivity is not satisfied. So we have a problem. Right? We're analyzing our equations, we're trying to understand why these equations are so difficult, and we are observing now a couple of problems. And the problem for the Stokes equation is that Bs is not coercive. And I can show this with a very simple example. So what I'll do is I'll choose one particular choice of a solution field U and a solution field P, and that's very clearly not going to satisfy the coercivity requirement. So I encourage you to kind of pause right now to look at these equations and think about what very simple example I can pick that shows that if I substitute that solution U and that solution for P into these equations, is going to show that this condition is not satisfied, that is not going to be larger than a constant multiplied by a norm. And so I encourage you to pause now and figure that out yourself. Okay, so I'm going to prove this by an example. And the example that I'm going to use is that my solution field U, P is going to be equal to 0, and it doesn't matter what I substitute for the P. Let me substitute the value 1. Or this is a function, right? P is a function, so let me be consistent in my notation. It's going to be the function x maps to 1. So for every location x in my domain, I'm just going to give it the value 1. Well, let's think about this. So I'm going to substitute. Okay, well, actually, no, I think that's a bad example. No, I'm going to leave this open. I'm going to say any function p. Whatever, it doesn't matter. Any function for p. So for U, I'm going to substitute 0. Now, that's allowed because 0 is in the space h1, 0. Has first derivative, clearly. I can integrate this, no problem. If the first derivative is 0, but that's fine. And for p, I'm going to substitute any function. Now, I almost chose the function being equal to 1. Of course, that doesn't satisfy my constraint that I just posed a second ago, that the integral has to be 0. So that's why I had to step back for a second there. Okay, so what happens if I now substitute this choice? And I'm going to substitute that in the bilinear form in both slots. What do I get? Well, what happens to my first term? I get the 0 here and a 0 here. So clearly this is 0. What happens here? Well, I have some p here. I don't know what it is. Could be anything in this space. But I have to multiplying this by the divergence of 0. Well, the divergence of 0 is equal to 0. Same thing happens here. I have some function, which again is p, right? I'm substituting this in both slots. So I have a p here. Could be anything, but I'm multiplying that by 0. So also this guy is 0. So if I substitute that, then the bilinear form, the Stokes bilinear form of 0, p, 0, p is going to be equal to 0. And 0 is not going to be larger than or equal to, so this is not true, not larger than or equal to, some constant, CB, where this constant has to be larger than 0, of the norm of, well, what is this? U, p. Or maybe I should say 0, p. Why is that true? Well, we know that a norm, by definition, the only way, and to be honest, this is the V norm, and I don't even know how to define the V norm, but it doesn't matter because I know that however I would define this norm or this kind of strange function space V, right, which was this combination of the H1 and this L2, and I don't know what this norm might look like, but I do know that if there, whatever definition of the norm I might choose, the only way that it's going to be zero is if the thing inside of the norm is zero, right? That was one of the definitions of a norm. And well, this is not zero. This is 0, p. The only way that I would have a zero norm is if it was 0, 0 and not 0, p. So I'm seeing here that my bilinear form in the Stokes equation for this particular choice is 0 for all choices p, which certainly does not satisfy my coercivity requirement that this is larger than or equal to some positive constant times that norm, which still involves p. So, with this very simple example, we've shown that the Stokes equation is in fact not a coercive weak statement. The Stokes partial differential equation does not lead to a coercive bilinear form. Now that's a problem. We said that coercive bilinear form guarantees existence and uniqueness of a solution and also was involved in the stability. But what we also said is that this is not a necessary condition for there to be a solution. I mentioned this, but I didn't spend a lot of attention to it at the time. I said that this was a sufficient condition. So that means that if the bilinear form is coercive, then a solution exists and it is unique. Again, assuming also these boundedness requirements. I did not say that that was the only condition that guarantees these, right? It's the difference between if and only if. And in fact, for the Stokes equation, that's immediately an example where we do not have a coercive bilinear form, but a solution does exist and the solution is unique. And what that is telling us is that our focus on coercivity might be too narrow. And it turns out that there is a more general condition that guarantees uniqueness and existence of a solution. So, coercivity is sufficient but not necessary. Maybe I shouldn't say so, I should say remember. Coercivity is sufficient. If we have coercivity, then we're happy, but it's not necessary. The sufficient and necessary condition are the inf sub conditions. Now, these are quite complex conditions, and that's why I haven't brought them up yet. And I'm also not going to write them out in this video. This is something that we'll get back to once we start talking about the Stokes equation, and that's going to be a couple of weeks from now. But it's something that I already wanted to illustrate because I want to show you that the tools that we've used so far can be used to analyze our partial differential equations. And in this case, the conclusion that we're drawing is that, well, the Stokes equation is not coercive. We need this funny inf sub condition. And what that means from a finite element perspective, that's actually going to be tricky, because if we have a coercive bilinear form, then we know that also our finite element approximation has an existing and a unique solution. So let me try to point that out. If the continuous, and continuous here means infinite dimensional H1 Sobolev spaces. So if the continuous bilinear form well, bilinear is what that's supposed to say. If the continuous bilinear form is coercive, then the finite element bilinear form is also coercive. And there exists a unique solution. And that's a pretty straightforward proof that I have lying around here somewhere. I'm not just going to point it out by the definition of coercivity. So coercivity is saying that this has to hold true for all functions in this space, for all of them. And what the finite element method really does is it only takes a couple of these functions in this space. It takes a couple of these head functions or linear combinations between these head functions. So if this condition is true for all functions in our infinite dimensional spaces H1, or here H1 0D times L2 0, if it holds for all choices, well, then it certainly also holds for this subset of choices which create our finite element function space. So that's why we like coercivity. If we can prove that the bilinear form corresponding to the true PDE without approximation, without numerical finite element methods involved, if that is actually coercive, then the finite element method is also creating a coercive bilinear form, which means that, based on the same theory, there exists a unique solution. This is not true for the inf sub condition. And that's why we typically don't like this condition. We prefer things that are coercive. Inf sub is a difficult condition to prove, and it's a difficult condition to work with. Because even after we've proven it, if we then do a finite element approximation, we have to prove it again for that particular finite element combination of spaces. And that's exactly why the problem comes in. We saw that for different choices of function spaces for U and for P, we get these funny patterns that are numerical, that are not physical. We got these checkerboard patterns. I've shown this a couple of times, I think, in the introduction lecture and in the lecture on prototypical equations. And that is coming from this. This is coming from the fact that the bilinear form is not coercive, as we have proven here, which means that all the theory that we developed in the analysis the functional analysis lectures about existence, uniqueness, and stability, we can't use that, but rather we have to go to these more complex conditions. And those complex conditions, we don't like those because they don't apply for or they don't carry over to finite element subspaces. And that's where the sensitivity with respect to the choices of finite element spaces comes in. Okay, so that's what I have in mind for this video. Now, maybe it's a bit of an anti-climax here. We've built up all this theory to be able to prove that bilinear forms permit unique existing solutions. And then the first equation that we take a look at is actually not satisfying these core requirements of coercivity. Nevertheless, I think that is maybe precisely the point, right? We're trying to understand where the problems come from. And in the case of the Stokes equation, well, that's exactly where the problem comes from. Nevertheless, the next equation that we'll take a look at we will be able to show that this leads to a coercive problem, or a coercive formulation, coercive bilinear form. And then we're going to also see that we have certain conditions on this coercivity, and that those conditions are going to be important for the stability of our system. And we'll get back to this inf sub condition and the required spaces once we start talking about the Stokes equation in more depth. Okay, thank you for your attention.